Hi, everyone. Thanks for joining, and thanks, Nadav, for inviting me. I am a bit about me. I did my undergrads and PhD at the Technion in Israel, and now I'm a postdoc at the Language Technologies Institute at Carnegie Mellon University. And this talk is about natural language reasoning with language models of code. Most people, most guests in this seminar will be talking about language models of code for code tasks. I think that this talk is a bit unusual because it's going to talk about how we use models of code for tasks that are completely unrelated to code. And most of the work that I'm going to talk about was performed by Luyo, Aman, and Chuyan, who are PhD students here at LTI. Peng Fei, who's a postdoc, and Yiming, Jamie, and Graham, who are professors here. And as you probably all know, language models these days are maybe at their historical peak of public popularity, thanks to applications such as GPT-3. However, more formally, language models are, we can think about language models as a function where, given a vocabulary of words, a language model is any function that provides a probability for every sequence of words coming from that vocabulary. So if our sequence of words is W1 to Wn, a language model can give us the probability for this sequence. So for example, if our words are Barack Obama was the president of the US, a language model might tell us that the probability of this sequence is 0.0012. For example. By the way, feel free to just unmute yourself and ask questions at any point. If I'm in the, if you're not sure, feel free to write in the chat, and the chat is open on my other monitor, so I will see it. So feel free to stop me if anything is unclear. We talked about language models. Now, most language models these days are autoregressive. They don't have to be, but most are. And this means that instead of computing the joint probability of the words directly, most language models compute the probability of the next word, wi, given all the prefix of words, w1 to wi minus 1. And then they compute the joint probability of all the words as the product of each conditional probability. So the conditional probability is the probability of a single word given the previous words. And what this allows us is to generate sentences word by word. So for example, if we don't know who Barack Obama was, we can just write Barack Obama was, feed that as the prefix of words, and ask the language model to predict the next word, or basically give us the probability for the next word, and then, for example, select the word that gets the highest probability as the next word. So for example, we can ask the model to generate the next word of the, and then given this new prefix, we can fit it again and get the word president, and so on and so forth. And eventually we get that Barack Obama was the president of the US. However, this doesn't always work as expected. Let me show you an example. So this is the Hugging Face Hub, and I'm going to query the Bloom model, which is a pretty large model that was trained on tons of natural language tokens. And given the prefix of Barack Obama was, the continuation that the language model provides was the first president to visit Hiroshima, and he did so in May of 2016, which is not exactly what we expected, right? You all can see my screen, right? Tell me if you don't. So it's not quite the answer that we expected. We expected the language model to just tell us who Barack Obama was, but instead the model told us a very specific detail about Barack Obama. So the common approach is to provide the models with a few examples in the prompt, or in the prefix of words that are given to the model to complete. So for example, we can tell the model that Mike Pence was the vice president of the US, and that Hillary Clinton was the Secretary of State of the US. And then we can, during test time in the prompt, without any further training, we can teach the model what kind of answer do we expect. And now when we press compute, the model writes that Barack Obama was the president of the US. It also completes new sentences about Donald Trump and so, but basically what I wanted to demonstrate here is that by giving the model examples in the prefix, it's called the prompt to the language model. By giving the model examples in the prompt, we can teach the model what kind of answers do we expect. So this is a kind of learning that is performed at test time rather than the standard training approach of that is usually used to teach machine learning models things. Sometimes in order to tell the model what kind of answers we expect, we show the model a few examples in the prompt, and only then we get the answer that we expect. Now, people have also trained and training language models of code basically for dozens of years, but maybe only recently, around 2 years ago, OpenAI's Codex model came out, which is the language model behind the GitHub Copilot plugin, which if you haven't used yet, I encourage you to use. It's really, it's maybe for the first time, it's really useful and time-saving. So basically, we can in the same way that we can train language models, we can on natural language, we can train language models on code as well that will complete our code and generate code for us. Now, a few months ago, we were wondering whether there are natural language tasks in which language models of code perform better than language models of natural language. And we found that there are such tasks. So for example, in the proscript task, our input is a natural language sentence or a natural language intent, such as serve the pot pies on a plate. And the goal is to generate this graph that shows all the intermediate steps that are needed to achieve the intent of serving the pot pies on a plate, where every node in the graph is a single intermediate step. And the edges are the chronological dependencies between the steps. Another example is the explographs dataset, where the input to the model is a belief, an argument, and a stance, which can be either support or counter. And the goal of the model is to generate a graph that uses the argument to support or counter the belief. Now, notice that such tasks require both the natural language understanding of what does each node mean and how to decompose the high-level intent into intermediate steps, but it also requires the structured prediction and the ability to generate complex graphs. Now, the standard approach in these kinds of tasks was to flatten or serialize the graph into a list of edges, sometimes in the dot format, if anyone is familiar with it, but basically it's a list of edges, and then either perform few shot, which is the few shot prompting, which is the approach that I demonstrated before with the Barack Obama question, by showing the model a few examples of questions and answers, and then providing the model with the new question and expecting the model to generate the same format of answers. So using a model such as GPT-3 or using the Blue model that I demonstrated before. Another option is to do supervised training with a model such as T5 and actually perform training of the model on many input-output pairs. However, the problem with these two approaches is that this kind of output of this kind of flattened graph is kind of unnatural because it diverges from the pre-training data that models such as Bloom and GPT-3 or ChatGPT were trained on, because it doesn't look like natural language that you can find in the wild. Another problem is that the sense of locality is quite different than in natural language. In natural language, usually things that are semantically related appear close to each other. So if we think about the hypothetical Wikipedia article about Barack Obama, we will probably see that Barack Obama was born somewhere, and then he did something, and then there will be a connection between entities that we'll see in succeeding sentences. However, in this kind of format, because we flatten a graph, it often happens that multiple occurrences of the same node are pushed farther apart from each other in this serialized format. So back to our question of whether are there natural language tasks in which language models of code perform better than language models of natural language, we found that the answer is yes, if you convert the natural language task into pseudo-Python. So instead of converting our graph into this flattened list of edges, our approach was to convert the graph into a pseudo-Python code. So as you can see, we define a pseudo class tree. It has no significant meaning, and we defined a variable named goal that has the string of serve the pot pies on a plate, and then we define each node, such as take pies out to cool, as an instantiation of the pseudo Python class node. It's not really a class that we defined anywhere. We just made it look like code. So we define all the nodes as instantiations of the node class, and then we define the edges as as a list of other nodes, and we put that into a pseudo field of a node called children, where the list is just the list of edges of other nodes that this node has edges to. And instead of providing this kind of input-output pairs to a model, to a language model of natural language such as GPT-3, we use few-shot prompting using a model of code such as Codex, the model that initially was intended for code completion. Finally, when the model actually generates this pseudocode for our test question, we can convert it back to the graph and measure how well the model did by evaluating the resulting graph using the same metrics that people have used before. So this conversion between graphs and pseudo-Python code is both reversible and lossless. In other words, we let the model generate code even when the task does not involve code at all. And we did find that language models of code, such as Codex, have a bit lower language modeling ability than language models of natural language, such as GPT-3. But we hoped that models such as Codex have a better structural understanding that will allow them to compensate for the loss in natural language ability. And we call this approach CocoGen, for models of code for common sense generation. And this work was led by Aman and Shuyan. And we evaluated this first on the two data sets that I showed before, the explographs. And this is how the pseudo Python code for this data set looked like. So in this case, the edges have types. So we defined the edges a bit differently as three tuples of source node, target node, and the type of the edge. And we compared our CocoGen approach in purple, which is based on the Code DaVinci 2. That's the newest version of the Codex model, at least the newest open source, not open source, maybe publicly available version of the Codex model, and also Text DaVinci 2, which is maybe the parallel language model of natural language, which is an improvement of the well-known GPT-3 model. Text Fury 1, which is a bit weaker version of the natural language model GPT-3, and T5 large, which is a bit different than the other models because it was fine-tuned. It is small enough that we can actually fine tune it by training it on actual 1,500 examples of inputs and output pseudo-Python graphs. While all the other baselines, the TextCurie, TextDaVinci, and our CocoGen models were prompted using the few-shot approach that I talked about before, and they got about 30 examples each in their prompt. So basically, they need to learn how to perform this task based on only 30 examples. So that's a bit of a trade-off that we have when comparing relatively small models such as T5, but we can fine-tune them on much more examples compared to much larger models that we sometimes cannot fine-tune. We can only provide them fewer examples in their prompt. And so we measured the semantic similarity between the generated nodes and the ground truth nodes, and also graph similarity between the generated graph and the ground truth graph. And as you can see, using our approach, CocoGen performed better than all baselines, even though the T5 large has seen many more training examples, and even though TextDaVinci is designed for natural language, and this is basically a natural language task. In the proscript dataset that I talked about before, where you need to put the potpies on a plate, the results were very similar, where CocoGen performed better than both versions of the textual GPT-3 and better than the fine-tuned T5 model. The last dataset is a bit different than the previous two. It's not about generating graphs anymore. It's more of a reading comprehension dataset where the input to the model is a paragraph that describes a process such as photosynthesis. And the goal is to complete this table where we have the entities that are mentioned in the paragraph. And we need the goal of the model is to tell which entity, what is the location of each entity in each state of the process. So for example, where are the water and the CO2 in every step of the photosynthesis process. And we also had to slightly change the template of the Python outputs. In this case, we defined a function for every step in the process, and every such function redefines the location of every entity, and that's also the format that the model has learned to generate for our test questions. And again, our CocoGen approach performed much better than the baselines. So why does it work?
A quick question. We assume there's only a unique way to do things, right? Like there's a unique graph that solves this task, right? This is an assumption that is hiding here.
Yeah, this is the assumption. I agree that it might not be true. But it's just, that's the kind of data sets that are currently available. But in general, and it's basically a limitation that hurts all models. So I agree that the real results might be higher because maybe the model has generated a slightly different graph that is also correct. But yeah, it's a limitation that we couldn't really avoid, and it hurts all models equally.
Thanks.
So why does it work? I want to remind you that we had natural language inputs and structured natural language outputs, but we modeled them by using code as a proxy and modeling the mapping between the inputs and the structured natural language outputs using a model of code. So we don't have like a proven reason for why does it work, but our hypothesis is that when we train a model on code, the model learns somewhat different abilities than a model that is trained only on natural language. So for example, this is a random piece of Java code. And imagine that we want to generate the expression that is highlighted in green. In order to generate this highlighted expression, which is short, it only has a few tokens, the model needs to actually perform a lot more reasoning than we think about first. So for example, in order to generate this expression, the model needs to know that stats is a variable that is available in scope, even though it was defined 4 or 5 lines above, and that this stats is an array, so it can be indexed, and this index can come from the row above, from the nearest for statement, and that this entire generated expression is going to be assigned into ret, which is an array of paths. So the model calls it the getPath method. So in other words, we believe that training on code makes the model better at some kind of procedures or long-range inference or some ability of connecting the dots. So it's not only predicting the next word, the model learns some higher level abilities. And actually connecting the dots is my favorite intuition for this. And another question is, what's more important, the code format or the code model? So the baselines that I talked about use the standard format, which used to be the state-of-the-art format of a list of edges, but it also used the text Da Vinci model, the textual version of GPT-3, while our CocoGen approach used the Python format and the different model of the Code Da Vinci 2 model. So this raises the question of what happens in these two cells, because our CocoGen approach is different than the baseline in 2 different axes. So here are the numbers for one of the metrics in one of the tasks. And as we can see, if we stick with the textual Da Vinci model and just change the standard format to the Python format, this doesn't increase the scores significantly. So just changing the Python format is not enough. And also, if we stick with the standard format, but to just switch the underlying model from the text Da Vinci to the Code Da Vinci model, this does give us an increase of 3.5 points. However, the combination of using the Python format and the Python model, the code model, gives us an improvement that is larger than the sum of each individual improvement. So this shows that this combination of models of code with pseudo Python formats is the key to address such tasks. Any questions?
Yeah, just if you can say something about the BERT score.
Yeah, I don't want to go too much into details because it's a bit, the BERT score computation is not that important, but it will take me a bit more time. So just imagine that it's any kind of score that we use to compare 2 sentences. So in this case, we use the BERT score to compare the generated nodes to the ground truth nodes, and it gives us some quite reliable, people use it very often these days, from a metric of how semantically similar are the generated nodes and the reference nodes. Yeah. I see a question, Guy.
Yeah. I was wondering, Uli, if you have some sense of whether, so obviously Code Da Vinci has seen a lot of Python as part of its training. And so you could imagine using other structures to also impart structure. It could be like something completely custom that represents a graph, or it could be like even again an XML or JSON or something. Do you have any like data or intuition as to whether it is the fact that you are using a structured output format at all, or is it also the fact that it's like Python is both a lot like natural language because it's Python, but also very structured?
Yeah, good question. So we did experiment with various formats for the pseudo Python code. I think that in the paper, in one of the appendices, we show all the different formats, and basically it didn't really matter. Any format that we tried performed better than the baselines. Eventually, we chose the formats that I showed in the previous slides just because they performed the best. But basically, all formats were quite good, and we did find that pseudo Python works better than XML or JSON. We believe that maybe the reason is that the model was trained on much more Python than XMLs or JSON, which sometimes are filtered out during the training of large models such as Codex. Yeah, so basically any format works. Some formats are a bit better than others. And by the way, I believe that this approach can be used for a variety of other tasks. People have talked to me about applying this to lab protocols, to recipes, so I believe that it can be used for a variety of natural language to structured natural language tasks. I see a few other questions here. So Lunyu asked, would different pseudocode designs affect the performance, like you have tried pseudocode in C++? Yeah, so I kind of answered that. We did find that Python worked better than C++, even though C++, it did work better than the baselines, but Python worked better. I think that the reason is that the designers of the Codex model from OpenAI have put more emphasis on training on Python. You can also see that in their paper that they cared more about Python. So that's why to work better for Python. Alon asks, have you tried, will it be possible to actually running the code in order to produce an answer instead of decoding the answer from the code format? Okay, great question, Alon. Alon asks if we can actually run the code instead of just decoding. And that's exactly what I was going to talk about next. So far, we showed how given natural language input and structured natural language output, we sometimes should convert our structured natural language output into pseudocode, and then use language model of code to generate code that represents this natural language task. And then we were wondering, as Alon was wondering, whether we can take these generated pieces of Python code and get additional abilities by running them on a Python interpreter. And one such task where this was especially useful is this class of mathematical reasoning tasks that you all have seen in elementary or middle school, where, for example, we have the question of the bakers at the Beverly Hills Bakery baked 200 loaves of bread on Monday morning. They sold 93 loaves in the morning and 39 loaves in the afternoon. A grocery store returned 6 unsolved loaves. How many loaves of bread did they have left? The common approach these days of addressing such tasks is providing the model with few-shot examples as before, but instead of just providing the model with the question and the final answer, the very popular chain of thought approach provides the model with the question and the chain of thought of intermediate steps that are needed in order to reach the final answer for every example in the prompt. So the actual test question that we care about is the question about the bakers at the Beverly Hills Bakery, but we also provide the models with a few examples in the prompt. So for example, one such example that we provide the model with the answer for is Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So instead of just providing the model with the final answer of 11, chain of thought provides the model with the all the intermediate steps. So Roger started with 5 tennis balls, 2 cans of 3 tennis balls each is 6 tennis balls, 5 plus 6 equals 11, so the answer is 11. And then the model performs much better for the test question because the model learns how to generate such reasoning steps for the test question and eventually performs much better on the test question. Now, notice that the problem with this chain of thought approach, even though it's super popular these days, is that this approach uses the underlying language model for 2 different roles. One role is understanding the question and decomposing the question into intermediate step, which is expected. We actually need the language model to do that. But the other unrelated role of the language model is actually solving each such intermediate step. So the language model is the one that actually performs the arithmetic of how much is 5 plus 6. And many recent papers have found that even though language models can sometimes do this kind of arithmetic, they actually struggle with long numbers and complex arithmetic. And even the Minerva paper, which is a 500 billion model by Google that was explicitly trained on mathematical content, has found that the two main types of mistakes are incorrect reasoning and incorrect calculation. So even after you train the largest model possible on explicit mathematical content, it still makes a lot of mistakes in the actual calculation in arithmetic. So instead of using the language model for the solving part, why don't we replace it with an exact solver, such as a Python interpreter? So the understanding part on the left will still need to be performed by the language model. That's the best way that we currently know how to decompose high-level descriptions into intermediate steps. But to do the actual computation on the right, we can use the Python interpreter. So we took the same prompts from the chain of thought paper, and we converted every answer to we basically converted every sentence in the answer to the corresponding Python statement. So for example, instead of just saying that Roger started with 5 tennis balls, we also added tennis balls equals 5. And then if 2 cans of 3 tennis balls each is, instead of telling the model how much is it, we just added bot balls equals 2 times 3. And the answer is, instead of providing the model with the final answer of 11, we just provide the model with answer equals tennis balls plus bot balls. And we don't even mention what's the actual final answer of 11. And then we concatenate the new test question, and we hope that the model will be able to do the same decomposition into natural language sentences and Python statements to the test question as well, and feed that into the language model. Now, the model generates the new interleaved sequence of natural language intermediate steps along with their Python statements. And finally, instead of expecting to get the final answer from the language model, we just take this generated Python code and feed it into the Python interpreter. And we get the final answer of 74, not by the language model, but by the Python interpreter. So in other words, instead of teaching the model to solve the question, we are teaching the model to write a program that solves the question once we feed that program into the interpreter. And we call this approach PAL, for program-aided language models. And this work was led by Luyu, Aman, and Shuyan. Are there any questions about the approach itself? Okay, feel free to write in the chat if there are any questions. So we evaluated this approach on a variety of such mathematical reasoning data sets, 7 overall. I'll focus on one of them, which is called the GSM-8K, which is maybe the most well-known one these days. And we compared our PAL approach, which is based on the CodeDaVinci 2 model, to a variety of other models that either use the same CodeDaVinci 2 model or use other, sometimes larger models, and that use chain of thought. So here are some of the results. First of all, we can see that direct Codex on the left, which just provides the model with a final answer for each of the prompt questions, performs much worse than Codex plus chain of thought, which is the blue bar that has a value of 63.1. So this just shows that chain of thought is extremely useful because it bumps the results by 40 points of absolute increase. Now, another interesting thing is that if we add a calculator to chain of thought, we didn't do that ourselves. This is the result of that we copied from the chain of thought paper. This increases the results of Codex plus chain of thought by 2.3 points. However, when we used our PAL approach, this improved the results by 8.9 points compared to Codex plus chain of thought. So both the blue bar, which is Codex plus chain of thought, and our PAL approach are based on the same base CodeDaVinci 2 model, but they use 2 different prompting approaches. And finally, PAL performs much better than chain of thought and better than the other baselines such as Palm, which is Google's currently largest and most popular model that has more parameters, and Minerva, which is of the same size but was explicitly trained on mathematical content. I see a question. Oh, no questions. Okay.
They're in the chat.
Oh, yeah, there are questions. So Shalev is asking how different is asking for a step-by-step answer instead of providing a step-by-step example. I don't have the exact numbers. I think that asking the model to answer step-by-step also performs quite well compared to like the zero-shot scenario when we just ask the question. But I don't remember the numbers. But I do know that providing the chain of thought examples in the prompt does perform usually better than just asking the model to think about it step by step. Alon asks, how did you convert the text with the chain of thought into code format? Is it still a few shot setup? Yes, we just had to do this once. We took the same prompts from the chain of thought paper and converted each prompt into the corresponding code format. We did have to do this manually, but it was just like 8 examples. So we did that once, 8 examples, converted them into the Python format, and then we used the same prompt for all the experiments across all the mathematical reasoning data sets. So I agree that there's some human manual coding here, but it's very small. Alex asks, do you have any sense how small you could shrink the model and still have reasonable performance PAL architecture? Yes, I'll talk about this in a few slides. Since you're now decomposing the reasoning step from the calculation step, it seems like it will be possible to train a very small language model to just learn how to do reasoning. Yes, great question, Alex. Maybe I'll just jump to that slide and then go back. Just a second. Okay, here it is. So as Alex asked, does it work with smaller models of code? So all the experiments, all the main experiments and the general approach was intended to use with the newest Codevinci 2 model, but we actually evaluated the same thing with, I'm not sure if they're smaller, but there are definitely weaker models of Codevinci 1, which is the previous version of Codevinci 2, and the Code-Cushman one, which we know that it has only 12 billion parameters. And in this case, what we can see here is that, first of all, the blue curve is our PAL approach. The green curve is chain of thought. And as we can see, the absolute numbers do decrease when we take a smaller base model, but the purple bars are the relative improvements between PAL and chain of thought. So as we can see, even though the absolute numbers are smaller, the relative improvement is quite consistent even with the small models. And another way to look at it is that it's quite surprising actually that as we improve the base models, the relative improvement remains around 20%, because many things in machine learning, if you add in any trick or any better representation, sometimes in machine learning, in many cases, as you increase the size or the power of the base model, the returns diminish until the gap is very small if you have a very strong model. And here, the interesting thing that we can see is that that the relative improvement remains consistent even with the strongest models. Jiang asks, for this task, is there a baseline that's fine-tuned on these data? Not directly, because I'm not aware of this GSM data set is a test set, basically. It doesn't have a training set. So I'm not aware of a baseline that's directly trained on such questions, but the Minerva paper was trained on billions of tokens of explicit mathematical content, mathematical papers, mathematical questions and answers. So the Minerva model is kind of the closest thing that we have for the model that you asked about. Lunio asked, for complex tasks that involve both common sense reasoning and mathematical reasoning, have you tested combining the methodology of both works? Interesting question. I don't have the numbers, but we did find that in these kinds of questions of mathematical reasoning, if we just do the Cocogen approach of just converting the answers into code without using the interpreter doesn't perform that well. So the first approach that I talked about in the first half of the talk about just converting the output to code doesn't work well in this case. It works very well when you need to generate structured natural language, but in these cases when you have the arithmetic to solve, you do need the extra step of actually using the interpreter. Logesh asks whether code models could generate multiple generations with a prompt. Few would be correct and others might be wrong. How is a particular generation is selected and scored in reasoning tasks? Okay, good question. In the results that I showed you before, we just let every model generate a single prediction. So this is greedy decoding basically. However, we also experimented with the so-called self-consistency approach, which is not that it's basically just as Logesh asked, just letting every model generate 40 predictions and take the answer that is the majority among all the answers in the same model and evaluate using that final answer. So even if even if the greedy prediction is wrong, the model might have 39 other predictions that are consistent with each other, and using the self-consistency approach, the other answer will be selected and evaluated. And as you can see, the gaps do decrease between PAL and the baselines, but PAL is still stronger by at least at least 2 points compared to all the other baselines. In this case, Minerva, the model that was fine-tuned on explicit mathematics, performed better among the baselines, but PAL is still almost 2 points better. Shalev says that I found that large language models have trouble with very simple arithmetic tasks, such as saying a quarter minus 1/8 equals 3/8. How can we explain this? They must have seen so many examples of such arithmetic tasks. Even with step-by-step, the reasoning is incorrect most of the time for that task. Yeah, I agree. That's exactly were exactly our direction of thinking. I think that maybe language models might just be inherently bad at doing calculations, because basically, like, intuitively, I think that these kinds of arithmetic questions require kind of understanding the logic behind it, kind of require understanding the algorithm behind doing such problems. So maybe language models are trained to generate the next word, or maybe there are other objectives, but basically they don't have the underlying algorithm to solve such problems. There were papers that explicitly taught the models how to solve the algorithm. So, for example, if you add two large numbers or multiply two large numbers, there's the algorithm that we all learn in second or third grade. So there were papers that showed that only if you explicitly teach the model to solve the algorithm, they can do better at these kinds of arithmetic questions. However, the model still had problems. So, for example, such papers have found that even if you teach the model how to add two 10-digit numbers, the models are not that good in extrapolating to numbers that are longer than 10 digits. So even if they learned the algorithm, they didn't learn the algorithm perfectly. So maybe we just shouldn't expect them to do the algorithm. Shalev has another question, but I'd love to discuss that later to continue with the talk. So far I told you about the GSM dataset, and a recent paper has found that this dataset is actually a bit skewed, and that 50% of the numbers in the GSM 80K dataset are one-digit integers. So we created another more difficult version of the GSM hard dataset, where we replaced every number with a number with a random up to 8-digit integer. And here are the numbers, where all prompting approaches use the same underlying model of Codevinci 2. So they, as you can see, the direct approach and the chain of thought, their results dropped by 63% and 75% compared to their own previous results, while PAL's results dropped by only 14%. So this shows that PAL is not only better on the standard benchmarks, it is also much more robust. And basically, since PAL offloads the actual arithmetic to the Python interpreter, it is kind of perfectly robust by construction, right? Because it doesn't really care about the actual numbers. It doesn't care if the numbers are 8 digits or 20 digits. As long as it can generate the program that solves that, and the programs will always be the same regardless of the actual values of the numbers, the Python interpreter will be able to handle any kind of number. And basically, since the Python interpreter is such a powerful tool, it is not limited only to addition and subtraction, right? We can do many more things using a Python interpreter. So we evaluated PAL on a variety of other symbolic and algorithmic reasoning benchmarks from the Big Bench Hard benchmark. So for one such example is, I have a chair, 2 potatoes, a cauliflower, a lettuce head, 2 tables, a cabbage, 2 onions, and 3 fridges. How many vegetables do I have? The way that we address this task is by teaching the model to generate a Python dictionary where the keys are the entities and the values are the quantities. And then the final result is computed by summing the values of this dictionary. And then this entire Python code goes into the interpreter. So basically, the language model learns how to convert the question into the Python dictionary format, which is quite an easy task. You just need to copy with the right format, and also filter and telling which entity is a vegetable and which entity is not a vegetable, which is also kind of an easy task for a large language model to do. But the final summation of all the values is performed by the Python interpreter. And as you can see, using PAL in this case gets us close to 100% compared to chain of thought and the direct approach. Another example, so if we have a Python interpreter that we can use, we're not even limited to Python primitive data structures like a dictionary. We can even use third-party external libraries and functions. So we taught the model to use external functions. So for example, if our question is 2015 is coming in 38 hours, what is the date 1 week from today in month, day, year format? And these questions are starting to be difficult even for humans. And we taught the model to use the datetime and date libraries. So we initialize the datetime, we teach the model to initialize a datetime object, and then we subtract the relative delta of 36 hours, and then we add the relative delta of 1 week, and eventually convert that object into the desired string format. And here are the results. PAL performs better than chain of thought. And basically we can teach the model to use any external library, and it's not limited only to the Python primitives. Here's the slide that I shown before following Alex's question. So I won't go over it again. It basically shows that PAL is beneficial with smaller or weaker models of code as well, but the benefit scales to larger models as well, and the relative improvement stays consistent across different models. Another interesting question in this spirit is, does this work with language models of natural language? So far we used the Code Da Vinci series, but we were wondering whether it worked with the Text Da Vinci series. And on the left, you can see the Code Da Vinci 2 results that we've shown before. They're just provided here for reference. And here are the results with the Text Da Vinci series. So first, we can see that using Text Da Vinci 1, chain of thought does perform better than PAL. But as the coding abilities of the Text Da Vinci model become better in Text Da Vinci 2 and Text Da Vinci 3, the benefit of PAL does improve. And so basically the answer is that it does work with language models of natural language, but they need to have a sufficient coding ability and code data in their pre-training corpus. And we kind of know that the Text Da Vinci 1 model did not have code, a lot of code at least in its pre-training data. Another question is regarding the exact format. A few questions were asked about the exact format of the prompt regarding the previous part of the talk. But in this case, we did a more comprehensive analysis of the prompt. So, do variable names matter in the Python code that we teach the model to generate? The blue bars are the baseline chain of thought, which is provided here just for reference, and the purple bars are our PAL result, the full PAL results that you've seen before. The orange bars are PAL, where we did not provide the model with the natural language intermediate steps. So we provide the model with only the Python statements, but without the intermediate natural language steps. This does decrease the results by a bit, but these orange results are still better than chain of thought. So we believe that even though we don't include the explicit natural language steps, by using the intermediate Python statements, the model implicitly understands also the intermediate natural language steps. But once we removed the variable names, the meaningful variable names, and renamed them into non-meaningful one-digit variable names, this dropped the results to be lower than, even lower than chain of thought. And we believe that the reason is that when we used non-meaningful variable names, the model was struggling with linking the right variable to the right entity in the code. So if the variable denotes the number of loaves of bread, by using a non-meaningful variable name, the model struggles with tracking which variable represents which entity in the code. So to summarize, in the first part of the talk, I showed how sometimes when we have natural language inputs and structured natural language outputs, instead of directly learning the mapping between the input and the output, we should better convert our outputs to Python code or pseudo-Python code and learn the mapping using a model of code. In the second part of the talk, I showed how instead of expecting the language model itself to provide us with the final answer, we can instead teach the model to generate a program that will give us the final answer once we run that using a Python interpreter. And I think that these two approaches raise a variety of interesting future directions. So for example, we're not limited to only use the Python interpreter once. We can think about a scenario when the language model is allowed to use the Python interpreter multiple times, and the execution result of the interpreter goes back into the language model that continues generating and using the Python interpreter multiple times. Another interesting question is what other classes of tasks can benefit from the seamless synergy between language models and interpreters. So far we talked about structured reasoning, common sense reasoning, and mathematical reasoning, and algorithmic and symbolic reasoning. But I'm honestly wondering what are the limits of and what are the boundaries of tasks that can benefit from these approaches. I believe that it's useful for any structured natural language task, any task where the input and the output have any structure can benefit from converting them to Python code. And basically, if we think about the Python interpreter as a tool that the language model can use, then this raises the question of what other tools can a language model use. One such tool that I believe in is retrieval. We've done some recent work about retrieval, especially in code generation, which is the focus of the seminar. So I'll very briefly talk about this work. We basically make the recognition that if you train a model in code in any point of time, the model will be only limited to use and call libraries and functions that it has seen in its training data. And the model will never be able to generalize to new libraries. And as new libraries and new functions come out every day, basically, the model that you trained at a certain point in time will never be able to use the new libraries and new functions in its predictions. So to address that, given a natural language goal, such as generate an HTML file with syntax highlighting, we trained a retriever that retrieves pieces of documentation. And then we trained a generator, either trained a generator or used a few-shot model. And this generator takes the original natural language intent and each of the retrieved pieces of documentation. And these pieces of documentation may contain libraries and functions that were not seen in the training data. And eventually the generator can generate code that calls functions and libraries that were not seen in the training data, basically by learning them using their documentation, similarly to how humans need to use something, and then they look for the documentation, briefly read that, and use these functions. And basically, if you think about other sources of retrieval or tools that language models can use, I believe that language models can use databases, knowledge graphs, APIs, and basically all the OpenAI models are now publicly available. So we can think about another model as a tool that a language model can use. So you can imagine one small language model that uses a larger language model if the small model, for example, is not confident enough, or maybe a general purpose language model that calls another domain-specific language model if the question requires any domain-specific knowledge. And that's it. We're 1 minute late, but I can stay a few more minutes if anyone has questions. Feel free to email me and ask questions if anything is still unclear. And all our code is available on GitHub. So thanks again. Thanks for listening.
Do we have any questions?
I see that on the chat, Alon had a few follow-up. Shalev and Alon had a few follow-up questions. Yeah, Shalev asked about how well can language models perform square roots. I don't know. Yeah, I won't repeat the question because I just don't know the answer. I don't think that anyone knows. Alon asks, following the 8 digits test, is it interesting? It is interesting. Why is there any drop at all for PAL? Yeah, good question. Why did we have any drop in performance for PAL? I go to this slide again. Yeah, good question. I believe that that the 14% drop is because sometimes the large numbers just confuse the model. They just confuse the model, and the model generates just an incorrect Python program. Following the daytime test, how well does PAL generalizes to challenges requiring other libraries which are not in the few-shot examples? Yeah, good question. We didn't test that. So in the prompts for this task, we did provide the model with examples that do use the datetime and dateutil libraries. I do believe that it will be much more difficult for the model to use kind of unseen libraries if they are not provided in the prompt. We didn't evaluate that, but I agree that it's harder. So I agree that it's a limitation of PAL in that sense, that in every benchmark in every kind of benchmark, we had to redesign the prompt and show examples that use the right libraries or right data structures. Shalev asked, what large language model are you using for these experiments? Mostly, we use the Code Vinci 2 unless stated otherwise. For example, in this experiments with the Code Vinci 1 and the Code Cushman 1, which are smaller. When in all the other experiments we use the Code Vinci 2. Alex asked, can you briefly summarize your efforts on retrieval for language models on code? What are you retrieving? Functions, lines, documentation? How do you retrieve? Appending to prompt, fusion in decoder, how do the results look? Yeah, thanks, Alex, for your interest. And unfortunately, I don't have much time. We can talk about this, or you can email me. The paper is also publicly available in the code. But just in overview, we retrieved pieces of documentation. We split the documentation into paragraphs just according to new lines, and retrieved pieces of documentation as much as the prompt of the generator could handle. We used different generators, so we used both models such as GPT style models that we did not that we either trained or used for few shot, and models such as Codex, which we could not train. Smaller models such as GPT Neo that we did train, and also fusion in decoder, as you mentioned, using models such as T5. So we did a variety of experiments. They're all available in the paper, and I'd love to take questions offline probably.
Okay, so I want to express my gratitude to Uri for his presentation, which was both interesting and educational. Thank you for taking the time to share your research with us.
Thank you, everyone, for joining us. Thanks, Nadav, for inviting me.